This is Mathias Bynens. His presentation is JavaScript Square Unicode, and he has a bit of a cold, unfortunately, so every time he coughs, just pretend he said excuse me, so we can move it along. I think that's basically all I have to say. There you go. Take it away, Mathias.
Okay, thank you. So yeah, today I'm going to talk about JavaScript, Unicode, and 90s gangster rappers. But first, this is me. I'm Mathias, and I work for Opera Software in developer relations. And both as part of my job and in my spare time, I like to collaborate on various open source projects that are somehow related to web standards. And one example of such a project is Unicode.js, which I started working on a couple of years ago. Now, what it does is not really that important for this presentation, but basically it does what you can see here. So if you enter an internationalized domain name, so a domain name which contains non-ASCII characters with accents or other special characters, it converts it into a pure ASCII version of that domain name. And this is important because at the DNS level, only ASCII characters are understood. So basically, Unicode is a hack that allows you to use internationalized domain names even though DNS would not otherwise support them. Unicode is something that web browsers and other software that deals with URLs implements. So I figured, hey, it should be fairly easy to write an implementation of this in JavaScript, right? Because I could just look up the specification for Unicode and follow the steps in the algorithm there. So it seemed fairly simple, but when I was working on this library, I found out that a lot of things were not really that simple because of the way JavaScript behaves by default. And I learned a lot of new things there, things that were new to me at least, and that's what this presentation will be about. But first, does anyone know who this guy is? You can shout. Yeah, it's Jay-Z. Everyone knows it's Jay-Z. He's a famous American rapper. But a little known fact about him is that at some point he tried to write a JavaScript program once. So he npm installed some dependencies and started programming away, but at the end of the day he had written a song about his frustrations with the language instead of the program. You actually may have heard this song before. It's called 99 Problems. Now, don't get me wrong, I absolutely love JavaScript, and even though I'm making fun of it here, but just like with any other programming language, you're just going to be surprised every now and then if you deal with it on a daily basis. That's just what life as a programmer is like. And that's also the reason why we have websites like phpwhatthefuck.org, which nicely documents all these weird quirks in the PHP language, and also whatthefuckjs.com, which does the same thing, but for JavaScript. And of course, everything on these websites can perfectly be explained if you just look at the specification, or for PHP, if you view the source code or read the documentation. But even then, if a particular behavior of a language is confusing to a lot of people, then that's a bit of a problem in my opinion, even though it may be possible to explain it. So I'm going to go ahead and say that, in my opinion, JavaScript does have a Unicode problem. Its behavior when it comes to Unicode is just really surprising, to say the least. But before we get into that, let's talk about Unicode first. Let's make sure we're all on the same page when it comes to Unicode. So I'm going to tell you the absolute minimum you need to know about Unicode, that you need to know to work with strings in JavaScript correctly, and nothing more. So don't worry, it's not too much. First off, it's easiest to think of Unicode as kind of a database that maps any symbol that you can think of to a unique number, an ID for that symbol called its code point, and to a unique canonical name for that symbol. And this way, you can easily refer to any symbol you can think of by just referring to the code point or to the name. So you don't have to use the symbol itself to refer to it. For example, Unicode maps the Latin capital letter A to the code point U plus 0041. Now, this is a hexadecimal number, and code points are usually formatted this way. They're zero-padded up to at least 4 digits, and then they get the U plus prefix. Now, another example is the Latin small letter a. This is a completely different character, so it has its own completely different code point. Now, I think you start to get the idea now. Each symbol in Unicode simply gets its own code point and its own name. It's as simple as that. And of course, there's a lot of weird stuff in Unicode. There's the snowman symbol, for example. I'm not sure why you would ever need that in your text documents, but it's there if you want to use it. And lately, there's been a lot of new additions to the Unicode standard, and there's, for example, everyone's favorite Unicode character is the pile of poo. And yes, that is the canonical name for that character in the Unicode standard. I would have loved to be there at that meeting when this was decided. Now, anyway, as you can see, the code point here is 1F4A9, which consists of 5 hexadecimal digits. So at this point, you may be wondering, how many code points are there in total in Unicode? What's the highest possible code point value? Well, the possible code point values range from O to 10FFFF. Again, these are hexadecimal digits, so that's 1.1 million possible symbols, a little over that. Now, to keep things a bit organized, the Unicode standard divides this whole range of code points into 17 planes that consist of about 65,000 code points each. And the first one of these planes is called the BMP, or the Basic Multilingual Plane. And this one is probably the most important one because it contains all the most commonly used symbols. Most of the time, you won't need any code points or any symbols outside of the BMP for text documents in English or Greek or Spanish or German. But because the basic multilingual plane contains all the most popular symbols, I like to refer to it as the notorious BMP. Now, anyway, just like any other plane, it contains about 65,000 symbols. So that leaves us with about 16 other planes, about 1 million other code points that have the group name as well. They're called the supplementary planes or the astral planes. So similarly, if someone is talking about an astral code point, it just means it's a code point that does not belong to the BMP, to that first important plane. Now, these astral code points are pretty easy to recognize because you need more than 4 hexadecimal digits to represent them. So as soon as you need more than 4 digits, excuse me, then you can be sure that it's an astral code point. And why is Unicode so important? Well, it's very useful in the context of character encodings, for example. Character encodings define how strings of text end up getting stored as bytes on your computer. And thanks to Unicode, all that a modern character encoding needs to do is just to provide that mapping from a Unicode code point to a sequence of bytes. So here's an overview of encodings that fully support Unicode. You don't need to remember all this, but these encodings can encode and decode any Unicode code points, that whole range of code points. So this table shows the number of bytes that each encoding requires per code point. And one of these encodings is a fixed width encoding. Which one would that be? Yeah, it's UTF-32. As you can see there, it doesn't care what kind of code point it is or what symbol it is. It will always take up 4 bytes of storage space for each and every symbol. So that's nice and consistent, but it's not very efficient in terms of storage space, of course. So most other encodings are variable width encodings rather than fixed width encodings. For example, there's UTF-16, which uses 2 bytes to encode a BMP code point. That's that top group of code points there. And then it takes 4 bytes, twice that amount, to encode an astral code point. So this is already slightly better in terms of storage space, but it's a bit inconsistent. Now, whenever you have a choice, you should always use UTF-8, and I'm sure you've heard this before, but there are several reasons for that. For starters, it supports full Unicode, just like all the other encodings in this table, but it's also optimized for storage space. As you can see there, some code points just take up 1 byte in UTF-8, and those are the ASCII code points. That means that UTF-8 is also backwards compatible with ASCII, so any existing ASCII text document that already existed before UTF-8 was invented is already compatible with UTF-8. Now, if you want to find out more about these encodings, it's very tempting to just Google for the name of the encoding, and then you'll usually end up at a document like this, which is an RFC, or a requests for comments document. And these are the documents that originally defined these encodings. This is the example for UTF-8. Now, however, most of the time you don't really care how the encoding was originally designed. It's far more interesting to see how software implements it today and how it's being used in the wild. And for that reason, you probably shouldn't look at those RFC documents. There's a much better document for you to look up. So all this is documented in the encoding standards. So rather than a theoretical design document like those RFC documents are, this document is based on the actual implementations in web browsers and other pieces of software. And this is especially interesting as web developers, of course, because we're usually targeting browsers. And yes, sometimes there is an actual difference between the RFC and between this document. For example, UTF-8 was originally designed to support code points up to U+7FFF, which is a very high code point value, and Unicode never supported this many code points. So it's kind of pointless to implement this. And for that reason, real-world software doesn't actually implement this at all. So always use the encoding standard. Don't look at the RFC documents. Okay, so now that we have a basic understanding of Unicode and character encodings, let's see how that applies to JavaScript strings. For example, you may have seen things like this before in strings. You can use a backslash followed by x, followed by 2 hexadecimal digits. And now that we know about Unicode, it's easy to see what these 2 digits refer to. They refer to a Unicode code point. So, again, this gives us a way to represent a symbol and to use a symbol in a string without actually having to use the symbol itself. So this is just another way of representing a string ABC in capital letters. This is ABC in lowercase, but it can be really useful in occasions where you want to use a character that is hard to type on your keyboard, for example. Or you want to avoid encoding errors when the file gets saved using an incorrect encoding. Or if you save the file to a web server and that web server is not configured to send files as UTF-8. So in that case, you can use these escape sequences, and then you get the copyright symbol and the E with the accent at the top, and there will be no issues whatsoever. So this is fairly useful, but we're also kind of limited because we only have those 2 hexadecimal digits that we can use. So this can only be used for code points up to FF. Now luckily for us, there's another type of escape sequence called the Unicode escape sequence. It starts with a backslash followed by U followed by 4 hexadecimal digits. So in other words, this can be used for the entire range of BMP code points, that whole first plane that we talked about before. So for example, now we can also escape 2661, which is the code point for the white heart symbol in Unicode. So this is great. I mean, we can escape any BMP symbol whatsoever just by referring to its code point quite easily. But how does that work for those other characters, for those astral symbols? There's over 1 million astral symbols in the Unicode standard. How do we represent them using escape sequences in JavaScript? We need more than 4 hexadecimal digits for those, so this is not enough. Well, another way to phrase the question is, what about our friends the pile of poo? And other equally important astral symbols, of course. So how can we escape them in JavaScript strings if we can only specify up to 4 hexadecimal digits at a time? The answer is we can kind of do this, but it's a bit complicated. In ECMAScript 6, the upcoming version of the JavaScript standard, this will in fact be really easy because it introduces yet another type of escape sequence called the Unicode code point escape. So now you have a backslash followed by U followed by braces, and between those braces you can use any amount of hexadecimal digits you like. And of course, you only need 6 digits to represent any Unicode code points at all. So by using this type of escape sequence, you can easily escape any Unicode symbol based on its code point. It couldn't be simpler, really. But if you need something that works today and that is backwards compatible with ECMAScript 5, the unfortunate solution is to use this thing called surrogate pairs. So each escape sequence that you see here represents the code point of 1/2 of the surrogate. And when these 2 surrogate halves are combined, they form a single astral symbol. And one thing that is confusing here is that the surrogate code points don't look anything like the original code point that we're trying to represent. Like if you read this first line of code, you wouldn't really know that you're trying to represent a pile of code at all. You would have to calculate what the original code point was. And in fact, there are formulas that you can use to make that calculation. And here's what that looks like. Of course, you don't have to remember all this, but apparently you do need to know that this formula exists if you want to deal with strings in JavaScript correctly. So anyway, this whole concept of using a single escape sequence to represent BMP symbols, but then requiring 2 separate escapes for astral symbols, it's a bit confusing, and it has a lot of annoying consequences throughout the JavaScript language. So let's see some examples of that. Let's say you want to count the number of characters or the number of code points in a JavaScript string. My first thought would be to get the length of the string and use the length property. And indeed, in these examples, the length property always happens to reflect the number of characters in the string. But what I learned when I was working on Unicode.js is that this is not actually always the case. Let's try some other characters. Now, we can explain this here because the capital letter A has the code point U plus 0041, and if we represent it using an escape sequence, as you can see in the line below, and then you count the number of escape sequences there, you still count 1. And that's why the length in JavaScript is also 1. So if you look at it this way, and we try some different characters, this is the mathematical bold capital letter A. So it's a different symbol with its own different code point. And as you can see, it's an astral symbol as well. So now suddenly that string has a length of 2 instead of 1, even though there's only one symbol there in the string. And this is because these characters outside of the BMP are represented as surrogate pairs, as we've seen before, but also because JavaScript exposes each of those surrogates as if they were separate characters, which really they're not. And that's a bit confusing for us as human beings, because we generally think in terms of symbols or visible Unicode characters. We don't want to deal with this behavior that is exposed, that's supposed to be just an internal implementation detail. Now, another example is, of course, the pile of poo character. It's also an astral character, so it also has a length of 2 in JavaScript. And for the Americans out there, there's a very easy joke to be made here. But instead, I'm going to show you an example of where this actually breaks some stuff in the real world. I'm sure you're all familiar with Twitter, and I'm sure you know they allow 140 characters per tweet, right? And their backend doesn't mind what kind of symbol you're using. So even if you're using astral symbols, it still counts as one symbol, which is what should happen. But for a long time, they had a bug in their front-end code, in their JavaScript. They would simply get the length property of the string and then subtract it from 140 to count the remaining characters in your tweet. So for each pile of poo I enter, the counter here decreases in steps of 2 instead of 1. So because of this bug, you could only tweet 70 piles of poo at a time. It was really terrible. Now, luckily, they have fixed it since, but it's just an example of where this behavior causes problems in the wild. Here's another example. There's this library called Countable.js, which counts the number of words and paragraphs and characters in the text area, and then it displays those numbers elsewhere on your page. And of course, the first thing I did when I saw this demo page was to enter a pile of poo. And needless to say, it counted it as 2 characters rather than 1. And these are just some examples. I'm not pointing fingers here, but because this is really an honest mistake to make. But the bottom line is, if you're writing a JavaScript library or you're writing any JavaScript code at all that deals with strings, you kind of don't have a choice. You have to make it work with all kinds of symbols, not just with those in the BMP. Because sooner or later, one of your users will use one of those symbols, or they will use an emoji, which are all astral symbols, and you don't want your library to break in that case. So the easiest way to verify that you're doing the right thing is just to do what I did. Just throw some piles of poo in there and see what happens. Now, entering that pile of poo kind of felt like this, because I just almost knew that something would likely go wrong, you know? Yeah, so getting back to our original problem, how can it be done? How can we accurately count the number of symbols or code points in a JavaScript string? Well, one way to do it is to use a third-party library, like Unicode.js, for example. It exposes some utility methods that it needs internally, like the Unicode UCS2decode method. You can pass in a string there, and it will return an array of code points in the string. So if you then get to the length of the resulting array, you will get a more accurate result, because it will only count one item for each symbol in the string. But of course, this is not ideal, because you just want to count the symbols in a string in JavaScript, and now you just introduce a dependency to do that. That's probably not what you want. Well, luckily in ECMAScript 6, there's a built-in way of doing this. You can use the new array.from method, pass in a string there, and that will use the new string iterator, which is another new feature in ECMAScript 6. The string iterator is designed so that it automatically deals with these surrogate pairs for you. So it groups the surrogate pairs together and treats them as one whole single unit, just like you would expect. So if you do this, you get exactly the same result as before, which is more accurate than just getting the length of a string. Now, another way of solving this problem using other syntax, basically, is using the spread operator. This is exactly the same thing as what we were doing before, only the syntax is a bit different. Now, I've also made a tool that takes a string as input, and then it shows the escape sequences for any special characters within that string. So it's a bit similar to a hex dump, but except the output is always found in JavaScript in this case. Now, with this tool, it's really easy to tell which Unicode symbols the string contains exactly. Excuse me. Even if the symbols are non-printable or just white space, as you can see here. So what I've been telling you up until now about the Astral symbols and the surrogate pairs, you kind of have to deal with those at all times. You don't really have a choice because your users can input anything they like, or even if you consume some strings from a third-party API, they could contain characters like that. So you have to support them. You don't have a choice. But depending on your use case, that may not be enough. There may be even more that you should do. And of course, this depends. But for example, in this case, JavaScript seems to be telling us that these two strings are different. Manana is not equal to manana. But visually, there's no way to tell. The strings look the same to me. So if we're being really pedantic, then counting the number of symbols in a string is even more complicated. Well, I copied these two strings into the tool that I was just talking about, and this is what came out. So the first string has the code point f1, which is the n with the tilde character on top of it. And then the second string has a separate n character followed by the code point 0303, which is the combining tilde. So these are two separate ways, different ways of representing the same symbol. Unicode has lots of these combining marks in it, and they basically get applied to the previous character in the string. And the reason these combining marks exist is because sometimes you want to use several combining marks on one and the same character. So it would be a lot of work to go through all the permutations and add all those characters to the Unicode standard. So instead, you can just combine them yourselves and add them to any symbol you want. But anyway, we don't really care about this. We want to get the length of the string, count the number of code points in the string, and we expect a result of 6 for both cases, not 7. So how can we make that happen? Well, in ECMAScript 6, the answer is to use Unicode normalization. So every string has a normalize method that you can call, and you can pass in the Unicode normalization form. This is documented in the Unicode standard if you want to look it up. But basically, to get rid of these lookalike symbols that we had before, you use normalization with the NFC form. And after that, of course, we still need to account for these astral symbols and the surrogate pairs, just like we did before. But after that, we get an even more accurate result than before. Now, you can already use this today. It's already supported in Chrome and Firefox, and in Opera, of course. And then, if you want, you can make it work in all browsers by using the polyfill that I'm linking to at the bottom. It's called unorm. So this solution is even better than before. But is it perfect? Well, again, that depends on your use case. If you need to support crazy stuff like this, where basically a lot of combining marks are applied to the same character, well, you'll need to do a little bit more work, of course. Here, visually, I count 9 different symbols. But even with our crazy function from before, it would still count it as 116 separate code points. And it's easy to see why. Now, you can, of course, fix this if you want to. The most efficient solution would probably be to use a regular expression that removes all these combining marks from the string, and then you count the resulting characters just like we did before. But we'll talk about regular expressions later. Now here's another example just to make you think about this behavior. Let's say you want to reverse a string in JavaScript. It sounds fairly simple, right? And in fact, a very common solution to this problem is to just take the string, split it up into an array of characters, then reverse that array, and then glue it back together using the join method. And indeed, that seems to work in a lot of cases. Like if you reverse ABC, you get CBA, which is exactly what you would expect. If you reverse manana, where the n with the tilde is a single code point, it still works as expected. But now, if we try the other manana variant with the 2 separate Unicode characters, now the tilde suddenly gets applied to the A character instead of to the N character, which is probably not what you would expect, right? And similarly, if you reverse an astral symbol, you will get an unusable string, basically, because now you have the surrogate pair, but the pair is in the wrong order, which means the symbol won't even show up anymore. This is a form of data loss, basically. So even something as seemingly simple as just reversing a string becomes really tricky in JavaScript, especially if you need full Unicode support. Now, luckily for us, a brilliant computer scientist by the name of Missy Elliott came up with a bulletproof algorithm that accounts for all these issues. The algorithm goes, I put my thing down, flip it, and reverse it. And indeed, by actually swapping the position of any combining marks with the symbol that they belong to, as well as reversing any surrogate pairs before further processing the string, all these issues are avoided successfully. So thank you, Missy. Now, I wrote a JavaScript library called sRever that implements Missy's algorithm. And as you can see, it does handle these cases perfectly. So if you ever do need to reverse a string in JavaScript, it is possible. Feel free to use it. Now, I've been giving you some examples of this behavior, but it always boils down to the same thing, really. And it affects the whole JavaScript language. So any other string methods that already existed before ECMAScript 6 will also have broken behavior here. So, for example, String.fromCharCode allows you to create a string from a code point. So you can pass in a number value, and it will turn that into a string that contains that code the symbol that that code point belongs to. But this only works the way you would expect it to for code points in the BNP range. If you try to pass an ASCII code point value, you will still get a result. It will throw an error, which might be explainable. But it gives you a result, but not the result that you expect. So be very careful if you ever use this. Now, if you want this to work properly, the solution in ECMAScript 5 is to use surrogate pairs once again. So you have to calculate the surrogate pair yourself using those formulas that I showed you before and pass them as separate arguments to the function. And only then will you be able to create piles of poo in your strings in JavaScript. Now, another thing you could do is to use a third-party library that implements those formulas for you. Like Unicode.js has utility methods for this. You can just pass in an array of code points, and it will turn it into a string. So it will basically do those formulas under the hood automatically. But still, this is not really ideal, because suddenly you have a dependency just from creating a string based on a code point value. It should be simpler than that. And for that reason, in ECMAScript 6, there is a new method called String.fromCodePoint. And basically, it's like String.fromCharCode, except it works for all Unicode symbols, not just for those in the BNP. So from now on, you should only use String.fromCodePoint and never use String.fromCharacterCodeAdd anymore. Another example is the String.prototype.characterAdd method. If you use characterAdd to retrieve the first symbol in the string containing the pile of poo character, you'll only get the first surrogate half instead of the whole symbol, which is probably not what you would expect. Now, there is no solution for this in ECMAScript 6, but there is a proposal on the table for maybe ECMAScript 7 to add something like the add method to the string prototype, which would allow you to deal with full symbols instead of surrogate halves whenever possible. So it would automatically deal with this for you. Similarly, character code add is affected as well. If you retrieve the code point of the first symbol in the string containing the pile of poo character, you'll get the code point of the first surrogate half, not the code point of the pile of poo. But in ECMAScript 6, there's now a built-in way of doing the thing you would expect to happen. It's called string.prototype.codePointAdd. So again, use codePointAdd instead of character code add. And if you want to support older browsers as well, just use the polyfill that I'm linking to at the bottom here. Now, another example, just to make you think about this issue some more, is let's say you have a string and you want to iterate over all the characters in that string and then do something with each individual character. In ECMAScript 5, you would have to write a lot of boilerplate code just to group those surrogate pairs together and treat them as one single unit. So it will look something like this. And in fact, you need even more code. This is not complete. Just to account for those surrogate pairs. But in ECMAScript 6, it's much easier, because now we can just use the for-off grammar, which will automatically use the string iterator internally. And like I said before, this new string iterator in ES6 deals with whole code points automatically. So you won't have to deal with surrogates anymore if you just use this. It's so much simpler. Now, there's many more examples, like string.prototype.substring, slice, basically anything that involves strings is affected by this behavior. So be really careful when using these things. And all of this is really unfortunate, but as Tupac would say, that's just the way it is, and some things will never change. Now, let's talk about regular expressions for a bit. The dot operator in a regular expression matches a single character, as you probably know. But because JavaScript exposes these surrogate halves as if they were separate characters, it will never match an astral symbol. So in this case, I would expect foo.bar to match the string foo pilot foo bar, but in JavaScript that's just not true. So let's think about that for a second. What would the regular expression look like to match any Unicode code point at all? Any Unicode symbol? Well, we can't use the dot operator as we've just demonstrated because it wouldn't match astral symbols and it wouldn't match line breaks either. We can solve the line break problem by using something like this, where we match all white space characters and then match all non-white space characters as well, so you would match all characters basically. But again, because JavaScript considers an astral symbol to be two separate characters, it still won't match astral symbols. So what would that regular expression look like to match any code point at all? Any ideas? Yeah. Yeah. Well, like this, apparently, yeah. It's kind of messed up, but the first part of the regular expression matches any DMV symbol that doesn't start a surrogate pair. And then the second half of the regular expression matches a surrogate pair or an astral symbol. So of course, this is not the type of regular expression that you would enjoy writing by hand. So I use the JavaScript library called Regenerate to generate this for me. And this is how you can use it. So basically, that's the one line of code that I ran. I created a new Regenerate instance, add the whole range of Unicode code points to the set, and then I call toString on that. And then it gives me a string that can be used as part of a regular expression literal. The reason it returns a string is because Regenerate is supposed to be used as part of a build script, so it can dynamically inject this code into your JavaScript files for you at build time. But it has some more powerful features as well. For example, you can create a new set, add the whole range of all Unicode code points to the set, so you would want to match all code points. Then you remove the range of symbols based on their string values, in this case the capital letter A to lowercase letter z, and then remove a single symbol, in this case the pile of poop from the set, and then turn that into a regular expression. Now, can anyone predict what this will look like? Well, I don't think so. I know I wouldn't be able to do this, but apparently it looks like this. So if I had to choose between writing those 5 lines of code or between writing that regular expression by hand, I definitely know which one I would pick. It's much easier to maintain or just to write that code you see at the top there. Now here's maybe a more practical example for you. Let's say you need a regular expression that matches all Greek symbols according to the Unicode standard. Because that's another thing that the Unicode standard does. It categorizes symbols and groups them together into scripts and categories and properties. Well, in this case, there are NPN modules as well that contain all this data straight off the Unicode standard. So if you combine this data with Regenerate, it's really easy to build complex Unicode-aware regular expressions. So here I'm just getting an array of all the Greek symbols according to Unicode 6.3.0, and then I feed that array into Regenerate, turn it into a regular expression, and apparently that looks like this. So again, not a regular expression that you would enjoy writing out by hand, let alone maintaining it. But you may have noticed that I'm using Unicode version 6.3.0 here, but Unicode version 7 has been out for a while. So let's imagine we have to update this regular expression based on the new Unicode version. Well, now that I have this simple script, all I need to do is just change the version number there, run the script again, and just like that, an up-to-date regular expression comes out. But changing that regular expression manually would have taken a very long time and would be very painful. So my advice is, if you need complex regular expressions like this, use a tool like Regenerate, for example, and save the script into a separate file that you can change later in case you ever need to modify the regular expression. But getting back to our problem with the dot operator, we want it to magically match astral symbols as well. How can we make that happen? Well, in ECMAScript 6, there's a new flag for regular expressions, the U flag, which stands for Unicode, and that magically makes the dot operator work more like you would expect it to. Now, another example is character classes. I'm sure you're familiar with ranges in character classes, like you can see here. For example, if you do A-C in a character class, you expect to match A, B, and C in a regular expression, right? And in fact, this is how it works. So similarly, you might expect this regular expression to match the pile of poo, the flex biceps, and the dizzy symbol, because that's the order these code points are in a Unicode standard. But unfortunately, in JavaScript, it doesn't actually work this way. In fact, you get an error when you try to execute the very first line of code. That very regular expression itself throws an error. So what is going on there? Well, you get a syntax error because the regular expression is invalid. The range is out of order in the character class. So what is happening there? Well, as far as JavaScript is concerned, this is what that regular expression looks like. So it just sees these two surrogate pairs. And now it doesn't try to create a range between those two ASCII symbols that you intended to use, but it tries to create a range between the one surrogate form in the first one and the high surrogate form in the second one, which is not the correct range in the first place. And because the first number is higher than the second one, this throws an error. Now, how can we make this regular expression work? Well, again, in ECMAScript 6, it's really easy. You just add the U flag to your regular expression, and then it just works the way you would expect it to. The bad news is that the U flag is not implemented in any stable browser yet, so you can't really start using this today. So if you want something that works today, you could use regenerate like we did before, and just manually, programmatically create a regular expression as part of build script, and apparently that would look like this, and then you can use that regular expression instead. But of course, it means your source code becomes less readable. So it would be much nicer if you were just able to use the ECMAScript 6 U flag for our regular expressions, keep our code readable, and still have it work in modern browsers. So I wrote a library called Regex. The U stands for Unicode, it's not poo, of course. That does just that. So it's a transpiler, basically. It allows you to write your code in ES6 using the U flag for regular expressions. It will go through your code, look for any regular expressions that use a U flag, and then rewrite them using ES6, using ES5 semantics. So it will still work exactly the same way, but it will work in existing environments. And there's a live demo of it online. You can try it out if you like. And it actually works in existing browsers. And the good news is if you're already using ES6 today, if you're using a transpiler like Tracer or Babel, perhaps, as part of your build pipeline, you can already start using the U flag as well, because both these transpilers use Regex internally to transpile these regular expressions for you. So in summary, I think it's fair to say that JavaScript has a Unicode problem, but rather than complaining about it like JC did, I think we should be doing more of this instead. Yeah, we should just deal with it and work around these issues, because really it's not that hard. I think the main problem is that people just aren't aware of these issues, just like I wasn't before I started working on Unicode.js. So the main takeaway here today is apply the pile of poo test. Whenever you write a piece of code in JavaScript, or if you're working on a library, or even if you're using a third-party library, just submit a pull request and add some piles of poo to the unit tests and see what happens. I think this is a great way to discover bugs in various pieces of software and to make sure, to help ensure that we're doing the right thing when it comes to ASCII symbols and that we treat all Unicode symbols equally. So yeah. So go forth and spread piles of poo. Thank you for your attention.
Thank you very much. All right, questions? Were we watching the same talk, or is it like clear for TV?
There's a question there.
Where?
Yeah.
Oh, well, raise it higher, man.
Hi, Matthias.
Hey.
Is there a way to programmatically establish whether a user is actually seeing the Unicode character you wanted him to see?
You mean in a web browser?
Yes.
Yeah, there's actually a neat way to feature detect this using the canvas element. So what you could do is you could take an emoji, for example, and you want to test if the user's computer can render a pile of poo emoji. So what you would do is you would draw that character as text to a canvas element, and then you would compare it to an unknown character. Like Unicode has some characters that are undefined and that will forever be undefined, so you could use one of those. And then you could compare the two renderings of those characters.
The reason I'm asking, sorry, can I, very quickly, the reason I'm asking is, you talked about the astral planes in Unicode, and in some of them, there are some amazing icons, you know, like arrows, and like figures that you can actually, when you design a website, you use them all the time. But you end up creating SVG fonts and using external assets. From your experience, could we, like, with the default font, with default system fonts, could we somehow try and use those? Or, like, because maybe in Windows, on Arial, and in Macs, with Helvetica, they're going to work. But what if on an Android phone, if the user has their Moto font? Is there a way for me to look up somewhere on the internet and say, I want to use this Unicode code point, which default fonts support it?
Yeah, there is someone who actually made a website like Can I Use, but for Unicode characters and code points. So he has this huge list of different browsers, including mobile browsers, that he tests each and every Unicode symbol in. And yeah, the support tables look crazy. Like it's green and red, and it's a mess. It kind of makes you want to use SVG instead. But of course, it depends on what kind of devices you really support in your product. So it could be something to consider. But the good news is in 20 years from now, we'll probably be able to do this if everyone switches to modern operating systems. Yeah.
Don't hope.
If you ask me about that link, that Can I Use website later, I can send you the link. I forgot the URL or the name, but I can look it up.
Okay, next question. No question.
Another question that I commonly get is, why does ECMAScript 6 add all these new methods and all these new functions to the string prototype rather than trying to fix the existing behavior in the first place? And the problem with that is it would be really nice, but it would break a lot of existing code that already relies on the broken behavior. And sadly, we cannot break the web. So for that reason, the only way to do it is to add new methods and new functionality, and we'll never be able to change the way these characters are exposed as separate. These actual characters are exposed as if there were two separate characters in JavaScript.
But the thing is, weren't there some functions that were forwards compatible, like character add, I think, where you mentioned some length wouldn't work, but there are some that could be extended to...
Yeah, but that's why we add, like, for example, from code point instead of
Yeah.
just fixing from character code.
Right.
So it seems like it's twice the same functionality, but it's actually not.
Okay.
It's just one is deprecated, and the other is what you should be using from today.
That makes sense. Right. Anybody else? You get one chance. Is that a question, or are you stretching?
I was just wondering, Matthias, have you calculated how many piles of poo you've thrown out to the web?
It's hard to say. I found a lot of bugs just by entering piles of poo anywhere. Even some security bugs every now and then. Like, actually, I use a custom keyboard layout just so I can type pile of poo by pressing two keys. Yeah. It's on GitHub if you want to use it as well. And just recently there was this cross-site scripting vulnerability that was discovered in WordPress, like every WordPress installation. And it was due to the way the MySQL database, so it has nothing to do with JavaScript, but because of how MySQL databases deal with Astral symbols by default. So if you use the UTF-8 encoding in MySQL, it's not actual UTF-8, it's just the BMP range of UTF-8. And anything else, as soon as you use an emoji, for example, it would say, hey, I don't know what to do with this, I can store this here, so I will just truncate the string here and insert anything up until this point and ignore everything else. And yeah, that's not a very good idea.
Why
So
am I
that-
surprised?
Yeah. So that led to a security vulnerability.
Anybody else? All right, everybody's stretching.
Okay,
I
thank
think
you.
we ran out.
Thanks
Thank you
for
very much.
joining me.